did. All right. So here was the question that I had that I started with it. All right. What would you call, just off your head, how would you call it? What would you call it? Point C in that pentagon. You said midpoint. Is it really a midpoint? A midpoint divides a line segment to two congruent points. So would midpoint be the right term? But I heard another one that was really good. Does the center make the most sense? Like, it's the most center location. Now, the reason why it actually is the center, okay? Now, here's why. If you sat there and I was to inscribe, remember we had the different terms inscribed and circumscribed last semester. So if I was to inscribe the polygon into a circle, and no, we have never formally defined a circle, but I think you guys will catch on because you know enough about circles already. See if I could do this a little bit better. Isn't C the center of that circle as well? All right, so that's why it's called the center of it. Now notice what it is. It has to be equidistant from the vertices. Well, where's the vertices? Where my two line segments or my two sides meet. So it's going to be equidistant. So you see all the congruency marks right there? Those have a name, okay? Those are called the radius. Now, the radius of the polygon, you will have a limited number. You will have one to each vertex. So you have 5 radii when you talk about a regular pentagon. Now, in a circle, how many radii would you have? You'd have an infinite number, one length, but would you be able to draw the radius anywhere you want on a circle? So notice it's limited when we talk about a polygon. So we also have the radius. We have another one. Now we have what's called the apothem as well. So a new term you've never heard before. Okay, the apothem is the distance from the center to the side. So in this case, this segment right here is your apothem. The apothem comes from the vertex, and it's going to be, remember it says the distance. When we talk about distance, we're always talking about perpendicular distance. But remember, the shortest distance from a point to a line is always the perpendicular line segment, right? So it's the length of that perpendicular line segment. Now, let's go there for a few minutes here. Let's just see if we can back up and see how much of information that you know. If I have radii of a pentagon, we know they're all the same. Do you guys agree with me that they make these lovely little triangles right here? Right? And what's so special about those triangles? They're always going to be what? Isosceles. So if I draw in my apothem like I do right here, what does it do to my side, like my segment FE? What does it do to it? Yeah, it goes to the midpoint, and so it's going to end up bisecting it. Exactly. We're going to have to use that to our advantage. Also, though, what would that apothem do to that angle FCE? Yep. So we know that these are going to be the same thing. All right, so we got a lot of stuff that we got in here. We still got more terms yet, okay? Then our next term that we're going to talk about is called the central angle of a regular polygon. So a central angle. Its vertex must be the what? Yep, okay. Now, so the vertex is the center of the angle, but also its sides are always going to be the radii, okay? So like right here, that would be a central angle. You're going to have the same number of central angles as you do number of sides. You have the same number of radii as you do number of sides. Are you guys starting to see the pattern a little bit? But when you work with this, do you see 5 isosceles triangles? Yes. Okay. The central angle, what I just drew here, HCD, it says it's on the center, it's a vertex on the center, and it has consecutive sides going to the vertices. All right, so it's called the central angle. Guys, think about central angle, vertex on the what? Center. But it has to have the radii making the sides. But you now have 5 isosceles triangles that make that pentagon. They're all the same size. So could you use the area of a triangle if you needed to solve for the area of this? Yeah, we could use the apothem and our side length to do that. Now, I'm going to give you a formula that takes care of all of that for you, but that's really where it all comes from, using that idea. All right, now the last thing that we need to know is we have to know how to find the measure of one of these central angles, because there's 5 central angles, we need to know how to measure. Now think about what you already know. If I have a point, how many degrees around that point is there? How many central angles did I have right there in that diagram? So what would you do to find this diagram's central angle? Yeah, 360 divided by 5. So basically 5 is the number of sides, right? Well, anytime I do this, it's just going to be my central angle is going to be 360 divided by n, the number of sides. So that allows us to do this. All right, so a few things you need to know because it's going to be huge. You need to know what the center is. So we know the center in this diagram, that's going to be point C. It's going to be the same distance away from all of the vertices and the same distance away from all of the sides, okay? You have an apothem here. Now, we only have one apothem drawn, but guys, could I have 5? Yeah, because couldn't I draw one from the center to every side? So you could have an apothem in any of those triangles, so just know that, but in this case, it's segment BC. We also have your central angles that are important to know. And those are any of them, remember, radii and the center is C. So I have here angle GCH, got angle HCD, got angle DCE, angle FCE, and angle GCF. Should I make that a G? All right, so you should have 5 central angles, but notice every one of those, very common, vertex, same thing. Now, there's one thing I haven't talked to you about that I use every single time I work with regular polygons when I'm looking for the area, and that's called the central angle triangle. So this is Mrs. Gregerson's addition to your book. A central angle triangle is really one of the triangles. I just pick one of the triangles out of the 5 that are congruent out. And so like the central angle triangle that I would use in this diagram is the one that has the apothem in it. So I'd say triangle FCE. And remember, make sure I put the E there. And so literally it would look something like this if I was to redraw it. Right? Notice the moment I redraw that, I draw the apothem in. Do you guys see any right triangles being formed? Do you think I'll probably end up using stuff with that? Yeah, so just remember, this would be your radius, this would be your apothem, this would be your whole side length, so common sense so far, and then this whole angle from here to here is your central angle. So that's why I call it the central angle triangle. It helps us solve anything that we need on. All right, so a lot of new terms, and it's just referring to them that you need to know those, okay? So when I work with this and I have a regular polygon, it's based off of any regular polygon. I can do this. I can do this for squares. I can do this for triangles. I don't like it for either one of those, but oh well. Hexagons are the ones we use mainly. We use a lot with hexagons, so make sure you know how to do those. But the formula is actually pretty simple. The area of a regular polygon with apothem A and perimeter P. Notice P is what? Capitalized this time, so it's the perimeter. It's the following. Area equals apothem times perimeter all over 2. Where that formula gets derived is basically I find the area of one of the triangles and then I multiply it by how many triangles they are, right? And that actually ends up calculating the perimeter, which you don't need to know all the Y's in it, but that's where it came from. Is the idea. Now, you could also, especially if you have nasty fractions, this is also a phenomenal way to do it so you can work with fractions easier. You might want to remember what P is. So remember, capital P, that's your perimeter. And guys, one thing you've done very well is making sure you don't change cases on these. So please don't now, okay? Make sure you do them right. And remember, perimeter is the number of sides times the side length. So remember, N equals number of sides. And S is going to be your side length. So keep those type of things in mind. Now, the first couple problems that we have here is to actually find stuff that would actually help us do and work with this formula. So we got to learn to work, we have to be able to work with them. N times S. Number of sides times the side length. Right? So now let's look at this next one. It says, find the values of the variables for each regular hexagon. Hexagons are the most common regular polygon you're going to use this formula for. And it's very important for the next chapter and the chapter after that. Okay, so make sure we know how to work with things. But when we do this, I'm going to sit there and I got to put in everything I know. And the most important thing you need to know is basically your central angle triangle. So the first thing I'm going to do is I'm going to draw one in. if I draw this in, and there's my central angle triangle, guys, what's the length of all the radii of this one? 8. So I know it's 8 and 8. So we know that is true because these are all the same. All right, now I want to find the apothem. For some reason they call the apothem P, but oh well, we'll get past that. I want to find the side length, which is Q, and I want to find that angle right there, which is X degrees. Well, the cool thing is I can find, see if this will let me do it, because it's not liking me lately. You always have to find the central angle first, all right? So remember, central angle is very easy to calculate. It's just 360 divided by what? How many sides do I have? 6. It's 60 degrees. Are we starting to see familiar numbers? Yes. Now, but what does the apothem do to it? It bisects it. So basically these two, so the big arrow says, oh, that's 60 degrees, but my apothem bisects it. Guys, what's X going to be? 30 degrees. Yeah, so X just ends up being 60 divided by 2, which is 30 degrees. If you said 30 degrees, great. Oh, look, it just created what type of triangle? 30, 60, 90 triangle. So what side of a 30, 60, 90 triangle do I need to find first? And I know which side. So how do I get there? Divide by 2. So I get 4. Oh wait, doesn't that make this other segment 4? What's the length of that whole side? 8. What's Q, my friends? All right, just 8 units, right? We don't know what's measured, 8 units. Okay, what's P gonna be? Yep, which is your apothem in this case, before root 3. Guys, it's as easy as that. Yes?
Couldn't as soon as you found that it was the central angle?
Yes. The reason why I don't want you to get in the habit of doing that, because that only works for hexagons. It only works for hexagons. But you're correct. It would always be that way. If it's a regular hexagon, yes. All right. So guys, let's work with this one real quick. What piece of information did they give you? Yeah, it looks like radius. You gotta be careful because if you radius, it has to go to the vertex. It has to go to one of the angles. So that's your apothem. So they gave you the apothem, and you're supposed to solve for everything else. Well, 80 degrees. You should probably be able to calculate that with no problem because isn't that your central angle? And again, I'm showing the work, but guys, it's to get you in a habit of always finding the central angle because you don't always have hexagons. 360 divided by 6, it's 60 degrees. All right, so we know A is 60 degrees. Wonderful. Now, wouldn't it make sense to redraw the apothem in my central angle triangle? Did you guys see how they drew the central angle triangle for us? So I'm going to draw that. What does it do to A? Bisects it. And I know that's going to be 4. All right, I still need to solve for the radius. I need to solve for the side, which we just discovered on the last one that they're the same length. But how am I going to get there? What side of that 30, 60, 90 triangle do I know? So how do I get to where I need to go? So right here, that means I got to divide by root 3. Does that mean rationalizing the denominator? If I'm solving for area, they're not asking for area right now. But yes, if we're doing area, yes. So we get 4 root 3 over 3. But what's the deal? I have to double that, right? Because aren't both of these 4 root 3 over 3? So what is that going to be? That means my side, 4 root 3, and I just want you to guys see it as this, or you can multiply by 2. Remember, if you add fractions with the same denominator, you just add the numerators. Isn't that just 8 root 3 over 3? Right? Units. Now, guys, what does that make your radius, which is C? Isn't that still also 8 root 3 over 3? Because remember, the short leg was 4 root 3 over 3. To get to the hypotenuse, you double it, it's 8 root 3 over 3. And we know on a hexagon, the radius and the side end up being the same, but that's only for a regular hexagon. All right, so guys, are we good with figuring that one out, right? Pretty quick and easy? All right, so let's do it with a couple different ones. So go to the next page for me. Now, the next one is actually a little bit easier Because they said these are regular polygons. So the moment I said it's a regular polygon, what shape is that first one? That's a square. So, I mean, you've got a lot of information you already know, but let's act like we're not as knowledgeable as we are. What's the first thing I'm going to ask you to calculate? Yeah, I want to look, you find the central angle. Well, the central angle in this case, isn't that 4? So all I have to do is go 360 divided by 4, and what do we get? So I get 90 degrees. So the measure of angle 4 is 90. Great. Got that in there. And you can even mark it like this if you want. Now I need to go ahead and solve for my other angles, because this one's all about angles this time. Guys, if 4 is 90, what do I know about this whole one right there? Isn't that also 90? So what's angle 1 going to be? Because your apothem's going to bisect it. So it's going to be 45. Guys, what's the measure of angle 3? I hope not 45. Should be 90, right? What's 2? Yeah, because we know this one's 45. That'd make that one 45, which makes sense. The shape that we're working with is going to have a lot of isosceles right triangles. Not hard, right? Because if you can find those angles, can I use special right triangles to find anything that I need? Yeah, so it makes it pretty simple. All right, now it says I have a regular polygon. So what type of triangle do I have if it's a regular polygon? Which is also, yeah, it's equilateral, so it's also equal angular. So again, I want to find my central angle first. Are you guys starting to see my little routine I have here? Yeah, I always have my central angle triangle, and I always find my central angle. So your central angle first is going to be 360 divided by, this time, 3. So did you guys get 120? So the measure of angle 7 is 120 degrees, which means this whole angle is 120. But what does your apothem do to it? Bisects it. So the measure of angle 5 is how many degrees? The measure of angle 6 would end up being? Yep. Now, be careful. Number one error people make on this one is they switch the 30 and 60 around. They mess up the short leg and long leg on equilateral triangles. Yes, sir? That's fine if you did that way. No, because you're still finding your angle measurements. You're still using what you know. Right? Aren't you? I mean, honestly, you are. Because if you drew in the radii like they did, you create 3 congruent triangles. Those would end up making congruent angles. It would totally work that way. I'm just doing it the way that helps you on this homework. Yes? Remember, if I didn't have the apothem drawn in, I have 3 triangles, correct? Those are all 3 the same size angle. So 360 divided by 3 would be 120. Does that help? No, this is the questions you guys need to ask so it makes sense. Good stuff. All right, let's start calculating this, okay? Of course, I go with one of the hardest first. Why not? Okay? So when we're working with this, make sure you draw a very rough diagram because you all need to see the visual, okay? That's one thing I want to do. Solomon, hood, please. I don't draw hexagons well. But I can draw it enough to know it's a regular hexagon, and if you need to mark all the sides, you can do whatever you need to do. So it just reminds you that it's regular. Great. And then it says side length of 6 centimeters. That doesn't help me much at that point. Now, I know that that's going to help me find perimeter. Great. But what's the one thing I want to work with? I want to work literally with just a small part of it. I want to work with that little triangle. I want to work with a central angle triangle and let all the work come from there. So I always redraw my central angle triangle. Okay, so here's your central angle triangle. Because when you do that, this becomes your side. So I know this is 6 centimeters. I know this is my radii, correct? Now guys, don't I have an apothem I have to work with as well? So I can draw my apothem in. I can start working with this pretty easily. What's the first thing you need to calculate besides doing that? Central angle, very good. So I'm going to find my central angle first. Yep, 360 divided by 6. You just end up memorizing this eventually. You just do. You just know. It's 60 degrees. What does the apothem do to that 60-degree angle, though? Cuts it in half, so that becomes 30. What does your apothem do to your side? So that becomes 3. What side of that right triangle do you now know? Which one do I need? The apothem. What's that going to be? See why we learn special right triangles now? It saves so much time instead of doing Pythagorean theorem. So great. Now, guys, do I need to know the radius? No. The nice thing is I don't need to know the radius, but I do need to know the perimeter. So the perimeter is easy, though. I have 6 sides because it's a hexagon. The side has length 6. It's just going to end up being 36. I have everything I need now. I have my apothem. I have the perimeter. You write down your formula. Put the work directly below it, not beside it, not above it, not somewhere else, directly below it. So I got here 3 root 3. The perimeter going to be 36 all over 2. Now, guys, here's where you don't need a calculator. 36 divided by 2 is 18. Go 18 times 3. You should be able to do 18 times 3 in your head. I heard it. 54 root 3. Do I have to label yet? Square centimeters. Are you guys starting to see the process behind this a little bit? Basically, what you did is you found the area of this triangle and I multiplied it by 6 is basically what you did. It just takes care of it in one formula. Yes?
How did you find that perimeter again?
I just took the number of sides times my side length. N times S. They just happen to be the same number this time. All right, let's try another one. All right, I have a regular hexagon again. And again, my regular hexagons do not look great, but it allows me to at least get that visual of what I need. My apothem is 5 root 3. So what am I going to draw? Central angle triangle. The apothem is 5 root 3 meters. I need side length. And that, by the way, my S's look like 5, so I put a little tail on mine. So I can find the perimeter. Peter.
Would it be possible to find the area of the triangle by doing 3 times 6?
Divided by 2.
And then multiply that by 4.
It's doing the exact, not 4. Multiplied by how many triangles would be there?
6.
Thank you, by 6, yes. That's what our formula does. It does it all for you, so you don't have to. It's exactly what to do. That's where the P comes from. It's the perimeter of the whole thing, because that's what we're getting it from. All right, so guys, central angle. Don't I have to do that next? What's the measure of central angle? You should have just have it memorized almost already. 60. So that creates both of those to be 30, because I know the whole thing's 60. Oh, what side of that 30-60 triangle do I know? Long leg. Which one do I have to go to? Well, if one of those segments is 5, what's the other one? So what's your length of your segment? 10. Perimeter, easy to do now. Remember, it's number of sides times the side length. There's just 6 times 10. I got that to be 60. Now it's just plug and chug into your formula because we have all the bits of information that you need. So your apothem is 5 root 3. Your perimeter is 60 all over 2. Well, that's going to give me 150 root 3 square meters. It looks confusing at first, but once you start knowing where the terms go and how the angles work, it's not too bad, is it? Did you see, like, when you have an octagon, though, how icky this will be? Because you'd have to use it with trigonometry instead. Yes?
For do you want us to write like central angle, or can we just write 360 divided by 2?
Well, as long as I can follow your work, that's great. I always put central angle just so you know what's going on. But remember, I'm teaching it. For certain, I want to see your central angle triangle, right? And I really do love, I literally look for perimeter and apothem before I ever look at your formula even. I like to see if you calculated them right or you found them correctly. I literally go point like this, point, point. Oops, if I can do it here. It's not letting me write. Point, point, point. Because if it's a harder one, I even give a point to the triangle. But the triangle gets you what? The apothem and the perimeter. Does that make sense? So like that's a 4-point question right there. But I can look and I can tell where you went wrong real quick that way. So you can lose a lot of points on this. All right, now the next one, guys, just because I just taught you a new formula does not mean you have to use it. Okay? Now, when it comes to squares, this is the dumbest formula on the planet. There's way better formulas to use for a square. Because when you look at this, it says find the area of a square with a radius. Now, my square should look better than that. It's not. Go with it anyway. All right, so here's my radius is 7. Do I really want to take the time and draw in a central angle triangle? Because if I extend my radius, can I find a diagonal instead? Guys, what's the length of that diagonal? 14. If that diagonal is 14, what's the second diagonal's length going to be? Can I just use yesterday's formula? I mean, excuse me, yesterday class formula, right? I can go area equals diagonal 1 times diagonal 2 all over 2. I am not going to mess with using a special right triangle when I don't have to. I know with a square the diagonals are congruent, so I can, and they're perpendicular, so I can use the formula for like a rhombus or a kite. So just go 14 times 14 all over 2. And what do you guys get? Is that 98? Someone double check.
196.
So it's 196 divided by 2. Is that 98? It's 90. It was 98, like I thought. Yeah, so it's going to be 98 square centimeters. It's as simple as that. Now, think about squares, guys. They're going to try to trick you. They'll go, oh, look, there's an apothem of 4. Find its area. Don't waste your time drawing a central angle triangle. What would you draw in instead? The other apothem, and you know its side length is what? Then you just go 8 times 8. Side squared. I mean, squares, this is not the best thing to use for squares. So I just want you to know, you need to understand how it can be done, but if it's not the best one to use for that shape, don't use it. Now for hexagons, this is the best way. Triangles, sometimes. Here's what I mean. It says here, find the area of a regular triangle with an apothem of 4 inches. Now, this one I draw the whole triangle out because it's just easier to draw than a hexagon. Make sure that goes here. Go. And they tell us, so I'm drawing my center in, apothem of 4 inches. If I did any old triangle, it's base times height over 2. So would I still have to draw in my central angle triangle to solve everything that I needed? Yes. I would love to use side squared root 3 over 4, but do I know the side length? No. So the fact is, you're still going to have to use the stuff that you know. So I'm still going to draw in my central angle triangle. I'm still going to solve, in this case, for my central angle. It's just 360 divided by 3 this time, which gives us what? 120. So from here to here, it's 120. So what does the apothem do to it, though? Makes that 60, right? It also bisects the side, which we need. All right, guys, what side does it know? Do we know of those right triangles now? Short leg, long leg? Short leg. I need to get to the long leg, right? Yep, 4 root 3. Now, remember when you first started doing special right triangles, how you hesitated? Do you guys hear how you don't hesitate anymore? You know the pattern. It makes your life so much easier. You're doing a good job with those. But I also know this is 4 root 3. So this whole side is 8 root 3. Perimeter is easy to find. So you got 3 times 8 root 3. And then it's just plug it into your formula. So in this scenario, do I think it's better than using like maybe our formula, like 1/2 base times height? Yeah, in this case, it's easier to use this formula. But could you do the other one? Yeah, let's talk about that once we get our answer down. Did I write that down right? Oops, I wrote 24, and I said 8 root 3, and it should be 24 root 3. Did not write that down right. Did you guys get on there? What did you get? I think the math is wrong somewhere. 8 root 3 times 4 is 24. Apothem is 4. Yeah, no, I'm doing it right. All right, it should be 24 to 12. Did you guys get 48 root 3 or something like that? Okay, I think it's 48 root 3. I'm going to sit there, and it should be square inches if we did it right. Yeah, because it'd be 12 times 4, right? So it'd be 48 root 3 square inches. All right. So working with this, my friends, not hard math. Someone said, could I use 1/2 base times height? Yes. The problem is you have to find the what? But it's not too bad. Really, you just need to know the radius. Well, guys, isn't that just going to be 8? Because that's the hypotenuse. So if that's 8, I know the whole thing is then what? 12. And then could you use 1/2 base times height? So is that a valid way of doing it? You just don't calculate perimeter instead. If you see it that way, great. Go for it. You just have, it's just work, right? And now, again, the moment I know 8 root 3, could I plug that into side square root 3 over 4? Yeah, so it's just a formula you could do. All right, guys. Why don't you do the next one on your own? Okay, let's do the next one on your own. And go from there. Okay, what time is it? I'm gonna make sure we get out of here on the right time. I'm gonna pause. All right, guys, did you get it right? All right, I'm glad. This one, again, that's a nice one to do, a way of doing it. Honestly, you just hope and pray they give you the side of the equal hour triangle and you can use the equal hour triangle formula, but those are options. Now, let's just change it up a little bit. It says, find the area of each regular polygon to the nearest square inch. Notice it's not a square, it's not an equal hour triangle, and it's not a hexagon. But notice what they gave you. What did they give you? They give you the pothum and they give you the side length. How hard is that going to be really for us to do this? Not. The main thing that you have to calculate, isn't that going to be just your perimeter? Yeah. Well, you don't need a central angle on this one because they already gave you the pothum. They gave you everything. As long as you know side length and a pothum, do I need to know central angle? You don't, because you actually have everything you need. So the perimeter, guys, how many sides is this first one? It's an octagon, so it's 8, right? So you just got to go 8 times 5, which gives you 40 inches for the perimeter. And then you just have to plug and chug it into your formula. Make sure you write your formula down. So your pothum is 6, your perimeter is 40, all over 2. Awesome, thank you, friend. All right, so what did we get? 120? Is that 120? Square inches. Are you guys saying it right in your head now? Steph's going inches squared. Do you say square inches or do you still go inches squared?
No, well, every time I think about it, I'm like, Mrs. Gregson went out through.
But let's just go there. This might be something I can't win on, but I'm going to try. Okay, I'm going to try. All right, next one. What would you guys do?
Central angle.
Do I need to do the central angle? Because remember, as long as they give you a pothum and a side, do you need to do central angle? No, so I know my apothum, I know my side length, so perimeter is easy. It's just the number of sides times side length. And so I go here, is that a nonagon? All right, so 9 times 4.7. What did you guys get for your decimal for that? I always do so people know where you're doing it. A lot of people don't go n times s. I just do that there so you guys know where I'm getting this. Because remember, I'm doing this on a video. So if someone's not in my class, they'd be like, where did that come from? I'm just showing you. All right, what'd you guys get? 42 point something? 23? The rest is easy. It's just plug and chug in. Now remember, it says round to the nearest square inch. So you are going to get a decimal, but you've got to round. So we're going to follow our directions. So we got 6.5 is my pothum times 42.3 all over 2. If you punched it into your calculator, you're going to get this. Someone double check, make sure I punched it in my calculator right. Is that what you guys got when you put in your calculator? All right, but is that what they want the answer in? Because if you left it like that, guess what I'd count it? Wrong, because you didn't follow direction. Because it said they wanted it to the nearest square inch. Well, that's going to be 137 square inches. Guys, what do you think? Doable?
You round down.
All right. Doable, right?
You round down.